A short jumper cable is easy. What goes in comes out, minus a small drop. But a long transmission line is not a simple wire. So how do we predict what it does to voltage and current over hundreds of kilometers? Stretch a line to 500 kilometers, and its inductance and capacitance are smeared all along it. Voltage and current travel down it as waves. Energize it with the far end open, and the voltage at that end rises higher than what we sent in. The trick is to treat the whole line as a black box described by just 4 numbers, the ABCD constants. So, here is our plan. First, we will meet those 4 numbers and see what each one means. Then, we will watch them change as the line grows from short to medium to long. Next, we will see why a lightly loaded line can push its own voltage up. And finally, how these same 4 numbers let us chain a whole power system together. An entire line, captured in 4 numbers. Let's build them. So picture the line as a sealed box with 2 terminals in and 2 terminals out. Feed in the sending end voltage and current. Out comes the receiving end voltage and current. 4 complex constants connect them. The sending voltage is A times the receiving voltage plus B times the receiving current. The sending current is C times the receiving voltage plus D times the receiving current. Each constant has a clear meaning. A and D are pure ratios, close to 1 for a line. B acts like an impedance, measured in ohms, and C acts like an admittance, measured in Siemens. There is even a built-in check. For any line, A times D minus B times C always equals 1. It is a quiet safety net. Get the 4 constants right, and that simple relation will always hold. Now, what goes inside the box depends on how long the line is. Take 3 cases. First, a short line, under about 80 kilometers. Here, the charging current is so small that we ignore it. The line is just its series impedance. So A and D are 1, B is that impedance, and C is 0. Second, a medium line, up to about 250 kilometers. Now, the capacitance matters. The neat trick is to split it in half and place 1/2 at each end. This is the nominal-pi model. It gives A and D a little less than 1, B the series impedance, and C the shunt admittance. Third, a long line beyond 250 kilometers. Here we cannot lump anything. The line is a true wave, and we must use the exact solution. It comes from the telegrapher's equations, written down by Oliver Heaviside in the 1880s. The constants become hyperbolic functions of 2 quantities, the propagation constant and the characteristic impedance. As the line grows, the model grows with it. Let's compute 1. Take a medium line, modeled as a nominal-pi. Its total series impedance is 50 ohms of reactance. Its total shunt admittance is 4 times 10 to the minus 4 Siemens. We only need the constant A, which is 1, plus the product of Y and Z, divided by 2. Now, here is a good place to pause. Work out the constant A for this line. Take a moment. Here is the answer. The product of Y and Z is minus 0.02. Half of that is minus 0.01. So A is 1 minus 0.01, which is 0.99. Notice, it is just under 1. That single fact is about to matter a lot. Why does A being under 1 matter? Remember the strange effect from the start. On a long, or lightly loaded line, the receiving voltage can rise above the sending voltage. This is the Ferranti effect. Its cause is exactly that charging current, flowing through the line's inductance, pushing the far end voltage up. And the size of it is captured by A. At no load, the receiving voltage equals the sending voltage divided by A. Since A is less than 1, that voltage is larger. Engineers put a number on this, called voltage regulation. It is the percent rise in receiving voltage when the full load is removed. For our line, dropping the load lets the voltage climb by about 5%. Too much regulation, and equipment at the far end sees a voltage it was never built to handle. There is one more gift in the ABCD form. Real systems are not one line. They are a transformer, then a line, then another transformer in a chain. With black boxes, chaining them is effortless. Each element has its own ABCD matrix. To combine them, we simply multiply the matrices together. The whole chain collapses into one equivalent box with one set of 4 constants, and from those, 2 numbers fall out that operators live by: the voltage regulation we just met, and the efficiency, the fraction of the power we sent that actually arrives. A 500-kilometer line reduced to 4 numbers and 2 answers. So, transmission line models. We treat the line as a 2-port black box with 4 constants: A, B, C, and D. A short line is just its series impedance. A medium line adds half its capacitance at each end, the nominal-pi. A long line needs the exact wave solution with hyperbolic functions. Because A is a little under 1, a lightly loaded line shows the Ferranti effect and its voltage regulation. And because the constants form a matrix, we chain elements by multiplying them. 4 numbers describe a line of any length. That completes the transmission line. If this made it click, please subscribe, and I will see you in the next one.